Okay, so one of the things, oh yes, sorry.
Just a question. On the back of that worksheet, the challenge question, maybe like questions about
No, I mean, probably not quite that hard. That's why I called it a challenge question. You're capable of doing it, but it's a little harder than I would necessarily expect you to do. And honestly, even this question, most of the buffer questions are pretty like straightforward, just molarity type questions that I would ask you about. I didn't do anything with converting to grams. So if you don't want to use this one, we don't have to, but it's certainly one you're capable of doing. Does that make any difference in whether or not you work this one out? Do you guys care? Or did you just pick this one because,
It was just the first one I circled.
Okay. Would you rather me choose one that's maybe like more similar to what you would see on a test?
Yeah.
Yeah. I would say like the ones on the back, 8, 9, 10 are probably more similar to what you would see. pH. You know, 9's kind of a good one because it does, if we did the whole problem on number 9, it shows how to just calculate a general buffer solution and then what you would do when you mess with it. So we could kind of do both. So you just want to work through number 9. Is there, I think yesterday I worked through number 9 with some people in here. Was that you guys? Do you care if we do number 9 again, or would you rather me do a different one? Okay. So we'll do that. So we're going to do number 9 on FRQ number 5. So one thing I would encourage you to do, any problem that you guys are going to face, you want to start to look at it as there's like one of 3 things are happening. It's either just a strong acid or a strong base. It's just a weak acid or a weak base, or it's a strong acid being added to a weak base. And so those, like all of your problems are going to be one of those 3 things. Bless you. And if it's strong, then you're really just looking at like taking the negative log of your hydrogen concentration. There's not a lot you have to do with that. It's just figure out what your concentration is and then take its negative log. If it's only a weak, then you're going to be doing an equilibrium problem. And so you have to figure out which are the ions involved in your weak. So it could be straightforward. This is my weak acid. I'm going to put it into an equilibrium problem. Or it could be a salt, and you have to figure out, is it a weak acid or a weak base, and then put it in an equilibrium problem. And then the other instance is when it's going to be a strong and a weak together. First, you're going to have to do a reaction with some stoichiometry to figure out what is left. And then second, you'll do an equilibrium based on what's left. So every single one of your problems is going to fall into one of those 3 categories. And so if you can try to stop, and I'll show you, like I'm just setting it up so that then when we do one, I can say, see, this is what we're doing. So just kind of try to focus it on that's what we're doing. So strong, it's the negative log. Weak would be equilibrium. If it's a combination of the 2, first you're going to do reaction stoichiometry to figure out what's left. That says what is left. And then second, you'll do an equilibrium with what is left. Okay, number 9 gives us some information. It told us we have 0.10 moles of HCN and 0.07 moles of KCN. Before and then after so that's what we had to start with our buffer, and then it gave us some HCl that was added afterwards. So the first thing I want to calculate is what's my pH before. So I'm just going to deal with these numbers, and I need to know the pH of my buffer. If we had to just make a guess, would we expect the pH of this buffer to be on the lower side of 7, or like below 7 or above 7? I heard several say below. I would tend to agree. Why are you saying that? It's not a strong acid, but it is an acid. It's a weak acid. If it were a strong acid, this would not be a very good buffer. Because remember, you can't have any buffers that are with strong acids or strong bases. To be a buffer, it has to have a common ion, and it has to have a strong acid. A weak acid or a weak base. Sorry, I was looking for the answer steps.
If it's a strong base, can you still have a buffer, or is that very, very strong?
Same thing. You can only do it if it's weak. Okay, so the first thing we're going to do is we need to write an equation. Every single time, start with writing your equation. So what things are involved here? HCN and KCN, right? Are these guys going to form a reaction together? No. How do I know they're not going to react together? They have the same ions. So that means I'm not going to be doing a strong and a weak together. I'm looking at either a strong or a weak reaction. And hopefully that you've got your memorized, and we just talked about the fact that HCN is weak, so we know we're looking at a weak acid. So I'm going to do HCN, and it's going to make some CN minus. And so that's where this CN minus is coming into play. It's going to be that CN minus right there. And then this HCN here is going to be that HCN there. So I can't have a reaction with only one thing. So what do I have available for that HCN to react with? H2O. So I'm going to have H2O react with HCN, and I'm going to form, I'm going to try to find markers that work, CN minus, and what else? So we've got H3O plus. That's being formed in this buffer, so that's a good sign that my pH of this is going to be on the acidic side, which you had already put together because you recognized this as being an acid. So great work. So far I set up my equation. Now I need to figure out what my pH is going to be. In order to find pH, ultimately I'm always going to get to this step, but because this is a weak acid, I'm going to have to do equilibrium first in order to figure out what the concentration is of my H3O plus. So I need to start it with what I have, what my information is. So do I know how much HCN I have to start with? Yeah, I have 0.10. But the problem with that number is my number of moles. And, whoops, that job me. That should be an equilibrium problem. So this needs to be an ice table, right? What's true about an ice table? Okay, so how can I get that number to molarity? Divide by my number of liters, which is very conveniently 1 liter. So it happens to be the same number of moles as molarity. But I just want to make sure you recognize that we still do divide by liters because it's not always the same. Okay, so that's how much HCN. How much H3O plus would I have to start with? 0. How much CN minus? Not 0. What? Because remember up here, I put in that many moles of HCN and this many moles of KCN. And remember that CN minus is this CN minus. So if I have 0.07 moles of KCN, I have how many moles of CN? 0.07. Yes, sir.
Why does the CN come from the KC?
And not what? Well, the HCN's on this side. Okay, so some of that is going to dissociate and it's going to make some more CN minus, and that's what we're going to find in our equilibrium problem. But we put in this much HCN here, and then we also put in CN minus by adding that KCN. Does that make sense? And then the K and the CN will dissociate and be left with CN minus. And so I'll also have 0.07 moles of K. I just don't care about that one because it's not involved anywhere. Does that make sense? Okay, so what do I need to do with my number of moles? Yeah, I'm going to divide by its number of liters, which still is, it's all in the same solution, so it's still all 1 liter. And so I got 0.07 molarity. Since I have some on both sides, how do I know which direction my reaction is going to shift? Will it shift forward or reverse? Why is it going forward? To make H3O, sorry. I got an email when I was paying attention to for a second. Yes, we have 0 here, so we have to shift it forward to make H3O plus. So I'm going to subtract X, I'm going to add X, I'm going to get, I don't care about water because it's a liquid, 0.10 minus x, 0.07 plus x. I have terrible handwriting. Okay, so then I need to plug it into my equilibrium expression. So I have x times 0.07 minus x divided by 0.10 minus x equals 2. Should I have it equal to a Ka or a Kb? A Ka, and so I need to know the Ka for HCN, which they told me is 4.79 times 10 to the negative 10. So does this look like a place I could drop my x's? Yes, ma'am.
So if you like were to do if you were given the Ka in the problem, then you were determined you need to use Kb, do you do that Ka times Kb equals like?
Yep.
And you would know that just because you'd have a foliage.
That would be the best place to look. Mhm. If we were doing the reverse of this reaction, you'd have to have switched it. Yes, it is. Thank you. I'm going to drop my x here in a second anyway, but thank you. So yeah, let's drop our x's and get rid of those guys there. And then we're going to solve for x, which I don't have the answers here in front of me, nor really a calculator that will calculate this well for me. So if you guys could help me out, that would be awesome. 0.1 times 4.79 divided by 0.07 gets me what? .6 times 10. Anybody else get that? What'd you get? 7.0.
That's probably right. 'Cause mine doesn't flow up that much.
It looks like that doesn't. Okay, you got 6 point what?
6.84 times.
I'm using my phone.
Okay.
Yeah, I mean, this one makes more sense to me. I don't even know. I could use my phone calculator, but. So we're thinking it's maybe that. Did anybody else do it? Nice.
I got 10. No, no, it's 10.
To the 10th?
Yeah, that's what I got.
Super. Okay, we're getting closer. All right, what does this number represent? Hopefully. Concentration of hydrogen. So what should I do with that? I'm going to take the negative log of 6.84 times 10 to the negative 10th. I'm going to get some number a little less than 10. What do I get? Can't be right. Okay, so what did we get? We got 9.6, is that what we said?
1.6.
1.6. All right, so we're going with this as our pH. I think that I remember that being the right answer on the sheet. 9.16. So far, so good. Oh, significant figures. Let's look at those for a second. This number 0.07 here. Is it just 0.07? Okay, so this only has one significant figure. So really, I only have one significant figure here. I'm sorry, here. This one's got 2, and this one's got a 3, but that gives me only one significant figure. So honestly, my answer over here probably should be better written as 9.2. It's not very many significant figures for me to only give you one, but that's all I did. Okay, so far so good. If we just had a buffer, I just had a pure buffer, that's what I wanted to do, is calculate my pH of a plain old buffer. I have to have solutions of both. How come I couldn't just put an HCN? What's the point of a buffer? It's going to resist change. If I just had HCN, would it be resisting change? No, because the reason this can resist change is because I have both of these compounds. So when I add some hydrogen, it has the ability to react with the CN minus. If I add some hydroxide, it has the ability to react with the HCN. You have to have both components for a buffer. So that's why I had to put in both parts to add those pieces. If I had just a weak acid, I would have done this exact same problem the same way. I just would have had a 0 here instead. If I had just a salt, it would have been the same process, but reversed, and this would have been a 0. So you can see how those are different types of problems, but the process that we're doing on all of them are the same because they're all based on it just being a weak equilibrium problem. Can you see some similarities there? Maybe. All right. Well, let's look at the other half of this. We wanted to know what would happen after the reaction. So what I need to do is I'm going to add some HCl, I think. I'm going to add HCl, 0.001 moles of HCl to this solution. It doesn't say so, but we're assuming that it doesn't make any change to the volume because they would have told you one way or the other on the test, I would say, assume your volume is negligible or something like that. So now I have my buffer solution and we're dropping in HCl. So which of my categories over there is that going to apply to? I'm doing a combination. So first I need to do some reaction stoichiometry and figure out what that HCl is going to react with. So what is that HCl going to react with? The CN minus. So my HCl and my CN minus are going to do a reaction. Is it going to be an equilibrium reaction or just a forward regular reaction? Just a forward reaction, right? And I'm going to make some HCN, and that's really all we care about that's being made. If you see you're going to have some leftover Cl minus, we don't care about that. So I wrote myself another reaction just so I can help in my brain think about what's actually occurring during the first part where that HCl goes in and what is that HCl actually reacting with. Does that make sense? So I know my HCl I'm putting in 0.001 moles because that's what they told me in my problem. How many moles of CN minus would I have to start with? What? I don't know. What did you say? I think so. 0.07. 0.07 moles, because remember, this is what we had to start with. Dropped in our HCl. And so they're going to have a reaction where they're going to come together. And my HCl is going to react with as much CN minus as it can. since I only have 0.001 moles of CN minus, I'm sorry, HCl, that's as much CN minus as I'll be able to react. So I'm going to react all my HCl, that's all going to react. And I'm going to react 0.001 moles of CN minus because that's going to combine with my HCl. So now how much CN minus will I have left? And then what other changes will occur because of this? I'm going to add 0.001 moles of HCN and Cl minus, but we don't care about Cl minus, to how much HCN did I have to start with? I actually had, you remember up here, we had our 0.10 moles. So now when I add to that, I'm going to get 0.001 moles. I'll let you think about that one for a second, because I see some questioning faces. Which zero am I doing wrong? Ah, I see. Thanks. Okay, so then if we were going to, is that what our questioning faces were? Was because I found a zero out of nowhere? Okay, good. That was a good place to have a questioning face. This one, in significant figure world, there's 2 places here and 3 places here. So when we go to add them together, you really should only have 2 places in the significant figure world. And so this question, you really should go ahead and round that to 0.10 moles if we were looking at significant figures. And then over here, we have 2 places here and 3 places there. So we really should round that to 0.07. Now, if we did that, then this would be a wasted problem because it would just be like the last one. So really what happened is whoever wrote this question didn't do a very good job of thinking through significant figures. So we're going to just go ahead and go with it. But I just wanted to make a point of that. Sorry. Fair enough? Okay. So now that I've figured out, this is what I mean when I said first you have to do some reaction stoichiometry to figure out what happened. Whether this was a titration or a buffer or any problem you could do anything with, you just first have to say, what is the strong acid going to do? Now I can see what's left. I've got some CN minus and I've got some HCN. So now I can run a weak equilibrium problem. My weak equilibrium will always start with the weak acid or the weak base if I have any amount left. The only time you wouldn't start with your weak acid or your weak base is if this ended and it were 0. That's the only time you don't, and then you have to start with its conjugate and turn it back into weak acid or weak base. Does that make sense? Okay, so as long as this is here, now I can fill those back in and say, oh, sorry. This is 0.069. And then since it's 1 liter still, we're going to do molarity. And then everything from here on will be just like what we just did. Now I'm going to do the weak equilibrium part of it. Now it's an ice table. So that's why I had to switch it back to molarity. Do you understand why this is not an ice table and this is? How come I couldn't use an ice table down here?
That's moles, not.
And why did this have to be moles? Right, this is not an equilibrium problem. This is just a forward reaction. The question is how much of my strong acid, how many ions of acid are going to react with how many ions of base? And I had to know specifically that number in moles. Once I figure that out, now I need to know what's going to happen in my whole solution. So we put it in an equilibrium problem. Minus x plus x plus x. Are you just following my math, or do you guys have a question?
So did you say we're assuming that it's 1 liter?
Yeah, no, we are assuming it's 1 liter because it told us in the problem that it was 1 liter, and it told us the number of moles, but it didn't give us a volume that went with it. And so we are going to assume that the number of moles was negligible. increase in volume. What if I had told you it was 10 milliliters of HCl? But remember, it would be 10 milliliters added to 1 liter. So now I have 1 liter plus 10 more milliliters.
Okay.
If I just had made up a number,
You do your total volume.
you have to do your total volume.
Can you repeat that
Oh,
question?
that's-
Yeah, sorry, there's too many questions asking at a time. Yes. So let's say here, this HCl, we said we just added the moles and assumed it added no volume. But let's say this actually added 100 milliliters, it'll be easier. So if we had 100 milliliters of HCl that got me those moles, then you would have to add that number to your original volume, which was your 1 liter. So now you have 1,100 liters.
And then you back up to
Milliliters.
the ice table and divide by 1.1 liters.
Sorry. Did that make sense? I was just trying to answer the questions you guys were asking. But we didn't do that. We get to ignore that. Yes, ma'am.
So, on the bottom, that equation, does that CO minus at the end, like, are you saying like, that'd be your, wait, where did it?
Where did this CL minus? It came from this.
H, yeah, okay.
But it's a spectator,
So it doesn't matter.
so it didn't matter.
And then the CN minus, that's coming from the KCN because the K is dissociated, like why is the K not there?
Because it dissociated. It's also a spectator.
In other strong and weak problems, so when we're doing that first step of the reaction stoichiometry, like, do we have to multiply the
Yeah. So here I gave you the number of moles. If I hadn't told you the number of moles and instead I had given you, it's like 200 milliliters of 0.10 molarity HCl, the first thing you would do is find your number of moles and then plug that in here.
Is that multiplying the whole?
Yep. Because molarity is equal to moles over liters. So you would have to multiply. Great questions. Do you guys have anything else you want to clarify? Confusing people. Okay, so far so good. So then we would finish solving that problem. Good with doing that? Okay. So I'm going to erase my stoichiometry part. And so when I go to plug this in, I'm going to have my x. I'm going to go ahead and drop my x's right away. Equals. And then can I use my Ka or do I need to switch to Kb? We can keep it at the Ka. So it was 4.79 times 10 to the negative 10. So we multiply, divide, and I'm going to get what?
7.01 times 10 to the negative.
Okay, so then if I take the negative log of that, what'd you guys get? So pH is equal to 9.15. So before my buffer, my pH was 9.16. Now I added a little bit of HCl and my pH is now 9.15. Does that sound reasonable? Yeah, we would have expected my pH to go down some because we added an acid, but we wouldn't expect it to go down very much because this is a buffer. It has the ability to react with both ions, and so it's not going to go very far. Questions? Look like you have a question.
If you're paying attention to sig figs, would that affect the pH and it's 9.2?
Yeah, this is a hard one because we stopped paying attention to sig figs long ago, so I didn't really know what to do with that. But let's say you have two significant figures. That one's got 2, if we have it written the way this is. So then this would be 7.0. And so then when you do that, how does that affect this? Well, this would be 2 sig figs.
Oh, very good.
So it would just be if you take this negative log of 7.0 times 10 and 7.01. Does that make a difference? Because then it would, I mean, this is 2 significant figures. Every time I get a calculator, somebody takes it, and I don't have one anymore. It's still 9.15. So, yes, ma'am.
So when we're looking at like the strong means like you're doing a negative log and weak means you're doing equilibrium and the strong unit means you're doing both of like the reaction stoichiometry. Does that only relate to buffer solutions or is that with everything?
Any single problem I give you. The first thing you can look at is like what are the compounds that are involved? You know, kind of like we did here.
Yeah.
And then we said, oh, I only have HCN, so I'm just doing an equilibrium.
Okay.
And then for the second part of the problem, I said, well, now I've got HCN and HCl, so I'm going to have to do a reaction. And that's why I did that second one. So whether it's a titration or a buffer or a salt solution or whatever, they're all going to fall into one of these 3 categories.
Because not all of them are the same. Like you have to follow the same thing. Like in titrations you can have like a weak or a strong.
Yeah, so in a titration, it's still going to be a strong acid or a strong base reacting with a weak acid or a weak base. And in a titration, you would do this same process that we just did, exactly the same. Do your reaction, what's the strong going to be reacting with what weak, and figure out what reaction occurs first. And then with what's left over, run an equilibrium problem, even in a titration. The only difference is between a titration and a buffer is there's really not any. That's why. There's no difference. It's all the same. What other questions? You guys have another one you want to do?
On the AFL, the multiple choice, can you go to 13?
Maybe. Yes, ma'am.
Can I go to the bathroom?
Absolutely. 13 and 17 on the AFL. Okay, so 17 is kind of, I'm going to do that one first because it's quick. That's the one we were just, kind of goes along with what we were just talking about. And the fact is a strong acid can never be involved in a buffer. And hydrochloric, sulfuric, and nitric are all strong acids. So if you have your strong acids memorized, this question is very easy. So between now and Thursday, memorize your strong acids. Does that help with that question for everybody? I've gotten a lot of questions about that particular one, so strong acid. All right, so then during this one, if you have a 25 milliliter sample of 1 molar solution of acid 1, it's mixed with some NaOH, and then we add some HNO3. So first of all, what do we know about acid 1 from question 2? In theory. You have to first looked at this chart and looked at acid 1 here, and what do you notice about acid 1? It has the highest of our acidic pHs. It's all the highest, so it's got to be the weakest acid. So we know that acid 1 is a weak acid. So first, we're starting with that. And I don't know what acid 1 is. It could be any of the ones, so I'm just going to use HA to represent, like, it has some amount of acid in it, right? But we know it's weak. So then we know initially what happens is that weak acid reacts with my hydroxide. And so when it reacts, I'm going to form some A-. Okay, so now I have a solution that consists of HA and A-. I have a little bit of both present in solution. Do you know why I have a little bit of both present in solution? Okay, so I have, right, it's weak, it doesn't fully dissociate, awesome, so I still have some HA left. I didn't add as much, oh, I guess I did. I added Oh yeah, my molarity of my NaOH is less than the molarity that I had of my original. So I didn't add as many moles of my OH. So I also didn't react all of my HA.
So if you would have added like 1.5 molarity of OH, then you would have had more of the hydroxide.
Yeah, I would have had only A minus and a hydroxide left, and that would become a different question. Yeah, we won't do that. Okay, so now I have this solution that's got a little bit of HA and a little bit of A minus. So I have concentrations of both present. Next, I'm going to drop in just a few drops of HNO3. What do you guys know about HNO3? It's a strong acid because we have all those memorized. So it's our strong acid. So just a few drops of that are going to come and react with one of these things. When you have a solution that has a weak acid and its conjugate base, that's a buffer solution. So it has the ability to react. And so it's going to not change its concentration or pH very much. So that's why C is the right answer. The pH of your mixture stays about the same because you've got your conjugate base of acid 1 is present. And so it's going to react with that extra H. And so that A minus is going to get turned back into HA. And we're only talking about a few drops, so you're not going to see a very large change. A lot of thinking that happens with this particular problem. That's why I put it on your AFL. You're welcome.
Is it likely that we'll see something like that?
I mean, it's less likely now that it's on your AFL. Oh, that didn't work. Okay, ask me questions. This would be a great opportunity to ask some questions.
It's not about that, but could you work through like an equivalence problem from the worksheet? Or
I
whatever?
will happily. I don't know that I'll have enough time to finish it.
Well, I got to, well, for number one, like I got to the pH after 12 milliliters was added, but I just don't know what to do like for the next one at the equivalence point. I got started, but I'm just kind of stuck.
Yeah, no problem. I'll get us as far as we can and then just kind of like say, this is how it's similar. Because an equivalence point problem is going to be a lot like the buffer problem we just worked out.
Yeah.
So the nice thing there is I can kind of show you what I mean by how these problems are similar. Do you happen to have numbers in front of me? You could.
So it's a 25 milliliter sample of 0.100 molarity NH3. And then it gives you a KB of 1.8 times 10 to the negative fifth. And then that is titrated with 0.100 molarity of HCl. And then it wants the pH. And so I did, and then it adds 12 milliliters of HCl, and I did that part.
You said you were comfortable with that part.
Yeah, I did that.
Perfect. So we're going to do the equivalence point problem here on this. So I have NH3 and I have HCl. So which of these three categories would this relate to? Strong and weak. So the first thing I have to do is figure out my reaction that's happening, right? So what two things am I going to put together that's doing a reaction? Thanks. The things that are present in the question. Good job. So NH3 and HCl. See, I have a strong acid because we have those memorized and a weak base because we have those memorized. Is this a forward reaction or an equilibrium problem? Forward, because it's got a strong acid. Anytime there's something strong in it, it has to be forward. So then these guys are going to react. They're going to make NH4 plus and Cl minus. And Cl minus I'm going to cancel out. Make me a little net ionic equation. Do you know where that reaction came from? If this were the test, would you be able to do that reaction right there? There's like a really good chance you'll probably have to do that reaction right there. That's a pretty common one. Okay, so what do I need to know?
Molarity.
Okay,
Wait, so molarity goes into an ice table or moles goes
molarity goes into the ice table. So I have to know moles here. Do I know my number of moles of NH3? No, but I do know my molarity. And so I've got my number of milliliters and my molarity, and this is where I would use that molarity is equal to moles over liters to calculate my number of moles. So I'm going to take here my 0.025 times 0.100, and that'll give me my number of moles, which is what? And so that's my number of moles. The point of this is an equivalence point problem. So this is where you have to think a little tiny bit. What is the equivalence point? What is the definition of that?
Equal number of
So if my moles of NH3 is this, how many moles of H plus must I have?
same.
Has to be the same. And so I'm going to react equal amounts. So I'm going to get down here to 0 of that and 0 of that. How much NH4 should I have? Okay, so now I've finished my reaction point so I can figure out what's left. Well, the only thing I have left here is my NH4 plus. So what does my equilibrium reaction have to be around? NH4 plus. And what's the only thing I have available for NH4 plus to react with? It's got to be water. And now we just established this is an equilibrium problem. And so then I would plug my numbers in. I'll need to take this back to liters or molarity. So I'm going to use my milliliters here. And remember, I have that many milliliters this and that many milliliters of that. So now this is by 50.050. And then I'd solve my ice table.
Because you added the combined.
Yeah, to combine my 25 milliliters of NH3. And because my molarities are the same, my volumes are the same. And so I'd have 50 milliliters. Have a great day, guys.